Today we are going to talk about why e to the pi I equals -1. I've made this video to help my son, but I'm making it public in case somebody else might find it useful. In the comments you'll find some links to other videos I'm going to reference. The purpose of this video is to curate some other really good sources and give a high-level overview of what they say. Hopefully after we look at all the pieces and all the different points of view, e to the pi I might make a little bit more sense to you. This video is actually the first part in a series. In this video we're going to be looking at some perspectives on the origin of e. This will give us some background about where e comes from and how it's calculated. First place to start, there's a great video by the YouTube channel Euler's Academy. It's called The History of E. I recommend everyone watch that video. It gives a great in-depth look at how e came about. I'm going to briefly touch on it here, and we're going to start with the binomial theorem. So binomial just means two terms added together, in this case a plus b. The binomial theorem is what happens when we raise this to a power. I'm not actually going to go into the details on how you calculate this, but just know that the binomial theorem lets you expand this, so a plus b to the third power, to something like this. And you could watch the Euler's Academy video. I put a link in the comments, a description. And it's not really necessary to know how that works in order to understand e to the pi I, and I'm going to show you exactly how this plays out further on in the video. So again, if this is something you may already know, but if you don't, you can go visit the link and take a further look. The usefulness of the binomial theorem is that you don't have to sit there and calculate each of these multiplication steps for each successive power by hand. So if you had a plus b to the sixth, that would take quite a few steps. You would do a plus b times a plus b, and then you would get that answer. You would times it by a plus b again until you're doing it 6 total times, and the binomial theorem shortens this quite a bit. Another form of the binomial theorem is shown here, where we have 1 plus x to the n. This is a simpler case since there's only one unknown. Expanding this binomial results in the pattern shown below, shown in the video here. This screenshot's actually from a Veritasium video about how Isaac Newton contributed to calculating pi. The link for this video is in the comments. One thing I want you to take notice about this is to notice how this n, that's the power we're raising this binomial to, finds its way into the numerator of each of these fractions here, and that's going to be pretty important later on. So in the Veritasium video, they explain that Newton's big contribution was generalizing this. Newton found that you don't just need positive integers to go in the exponent. You don't need just positive whole numbers. You can put negative numbers, fractions. It doesn't really matter. The formula still works. That's a pretty important discovery, since that leads us to doing crazy things like putting irrational numbers like pi or imaginary numbers like I in this exponent. Okay, so now that we have some background, let's start moving towards exactly what e is. Historically speaking, e came from ideas regarding compound interest. In blue here, we have the compound interest formula with using 100% interest, which is this one here. And n is the number of times that we'd compound the interest each year. So if we compounded it 4 times a year, this n would be a 4. And increasing n has a effect of increasing the amount you get from the interest. At some point, though, somebody raised the question of what happens when you compound the interest an infinite number of times. As you may have noticed, this formula is expandable, just like any other binomial. It's in binomial form, just like this. It's exactly the same as 1 plus x to the n. Euler used this to approximate the exact value this would result in if n goes to infinity using binomial expansion. And today we know that number as e. So going back to the Euler Academy video on the history of e, we can see what this looks like as we expand this out. I won't go into the details. You can watch this the Euler Academy video if you're interested. But from here, you can see how it leads to some very nice cancellations. If we look at the red, which is the result of this, mostly all of our n's are gone. They've all canceled out in one way or another. The only thing we're left with are these 1 over n's right here and right here and right here. But as n goes to 0, as n goes to infinity, these all go to 0. So we're left with 1 times 1 minus 0, which is just 1. And same thing here, and you can have 1 times 1 times 1. So on all of our numerators, we have a 1. And on the bottom, we have a very nice pattern of 2 factorial, 3 factorial. And that just continues on and on and on like that. And the further out we go, the closer we actually get to the actual number of e, which is 2.71828, so on and so forth. So as you can see, e isn't just a number. It comes from a very specific binomial expansion that shows 100% continuous growth. It's also worth noting that e is not some special result. You can get any number you want with this formula just by changing the rate of growth. Right now we're using 100%. But if you change this to 69.3%, that will actually get you a value of 2 instead of 2.71828. So the result of e is just 100% growth in this formula, but it is not anywhere near a special result. You can put in any value you want, and depending on what you put in for that rate of growth, you will get any number. You can get anywhere from 1 to a million. It doesn't really matter. This formula can get you any number. It just so happens that they chose 100%, and that gets you e. Okay, so now let's start getting into the really good stuff. Let's look at e to the x. So here we could say that raising e to the x is the same as raising this binomial, where n goes to infinity, to x is the same thing as this binomial, raising to the nx. This is just because this right here is e, and this right here is also e, and what happens is when you have a power to a power, you just multiply the powers. So this is basic algebra right here. That's all that's happening. So let's take a look at the binomial expansion that created e again. I've marked here where the power of n has ended up in this expansion. All right, and please take a note that it's all in the numerator. All right, nothing's on the bottom. So what we're going to do is we're just going to change our power to x times n. I'm just going to pop it in here and make the adjustment everywhere x should be in this. So I'm going to put an x here, I'm going to put an x here, I'm going to put an x here, here, so on and so forth. So here I have what it would have been without the x, and it would have reduced to this. And again, I've marked where all the powers went. So we're going to see what happens when we plug in the x. Now, if you notice, all these n's are canceling, but there's nothing to cancel this x. So in all these spots, we would be left with this. Again, 1 over n, as n goes to infinity, goes to 0. But the rest of these become x's. So now if we take a look at our result here, we notice that we have basically 1 plus x, and then these x's multiply this x minus 1 over n is x minus 0, because 1 over n goes to 0 as n goes to infinity. So we have this really nice pattern where we end up with basically what we had with e, where we had 1 plus 1 over 2 factorial plus 1 over 3 factorial, except this extra exponent just gets put in front of what we had. So we have, instead of 1 plus 1 plus 1 over 2 factorial, we have 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x a third, and so on and so forth to infinity. So adding a power, I mean, you could add a y here too, and you're just going to end up with a very similar result, and it is not hard to calculate at all. The last thing I want to mention is what happens if I change my rate, and I'm going to show that it's really the exact same thing as if we add a power to this. So let's make this x over n. So our rate's going to be x, whatever that might be. And I'm going to change this accordingly. And I've changed where this part of the binomial goes in each of these spots here. And now let's look at the result. And the result is exactly the same as before. So it's the weird property of this that a rate and an exponent have the exact same effect. And we're going to want to remember that for later when we manipulate the formula of e to the pi I and what that represents, and it lets us shift things around into a more understandable fashion. So just keep that in mind for later on. Alright, so the last thing I'm going to go over is just a quick review of the complex plane. So if you remember complex planes, you have a complex number, maybe like 2 plus 3i, and we want to plot that on a graph. The y-axis will have your imaginary numbers, your x-axis will have your real numbers. Now, you take a complex number like 2 plus 3i, and the real portion is going to be 2. All right, so we're right here right now, and the imaginary portion is 3i, so we're going to go up 3i. And this is our point on the complex plane. Sometimes you might represent it more like a vector, where you're plotting the distance from the origin here. But for now, let's just think of this as a point. Some other things to review here is timesing by I. Let's say we start at 1. Timesing by I will rotate you 90 degrees in the origin, around the origin, sorry. Timesing that by I again will get you -1. Timesing that by I again gets you -I. And then you times it by I and you're back to 1. Moves you in a circle. Doesn't just apply to 1. You could do that with 2, 2i, -2, -2i, then back to 2 again. And timesing by I also would rotate this point by 90 degrees. So if we multiply this by I, you're going to get 2i plus -3. Right? So we have -3 plus 2i. So if we again look at this as a vector, you rotated it 90 degrees. And this will keep happening every time you multiply this by I until it goes around. Let's see, what would that be? That would be -3i, -2 minus 3i, so that would be right here. And you would continue to rotate around 90 degrees every time you multiplied by I. The final thing we're going to go over is what happens when you take a complex number and you raise that to a power. There's two things we're going to want to look at here. The first is, what angle does this form? Again, we're going to treat it like it's a vector. This is our point, some a plus bi. And let's say this forms a 30-degree angle. Let's also assume it has a distance from the origin of 2. So first here, let's square this. Let's see what happens when we square this. So what's going to happen here is we're going to move another 30 degrees. So whatever this initial angle is, when we increment the power, it's going to go an additional 30 degrees. The other thing that happens is this distance from the origin is going to be raised to whatever power we have here. So our initial distance from the origin was 2. And when we squared it, the distance from the origin is now going to be 4. Now let's take another example here. Let's say remove our squared here, and let's make it to the 3rd power. So now we had an initial angle of 30 degrees, and now we're going to increment it 3 times. So we're going to have one 30 degrees, a second 30 degrees, and we're going to have one more 30 degrees, and we're going to have a completely vertical line. Right, because we've gone 90 degrees. We had an initial 30, and then we raise it to the 3rd power, which means basically 3 times 30 here. Right, we're going to do this 3 times, and we're at 90 degrees. Now, as far as the distance from the origin, we started with a 2, and then we raised this to the third power. We should now have an 8. So this is going to be very pertinent to what we're doing with e to the pi I. So just try to remember that every time you raise this complex number to a power, whatever angle this forms is just going to be multiplied by this power. So in this case it was a 30-degree angle, but it could have been a 50-degree angle, it could have been a 60-degree angle, 150 degrees, it doesn't matter. So whatever angle the initial complex number forms, when you raise that to a power, it's going to do that angle this many times. So in this case it's 3 times, but if this was to the 5th power, we would be doing our 30-degree angle 5 times, and that would be at 150 degrees. And the other thing to remember is that distance from the origin, you have that initial distance from the origin of that complex number. When you raise that to a power, that distance is raised to a power. Depending on what this number is, it can either get further away from the origin. So anything greater than 1, if you're raising it to a power, it's going to get further away. Anything less than 1, if you raise that to a power, it's going to get smaller. So it's going to get closer to the origin then. So just keep that in mind, that we're going to go into that a lot more heavily in the future videos. So hopefully this will ring a bell to you. Hopefully you've done complex numbers. Otherwise, you feel free to review it, or hopefully you understand the explanation I just gave. And we're going to cover that in the next section. All right, that should wrap it up for this video. Thank you.